Itô calculus, named after Kiyoshi Itô, extends the methods of calculus to stochastic processes such as Brownian motion. See Wiener process. It has important applications in mathematical finance and stochastic differential equations. The central concept is the Itô-stochastic integral, a stochastic generalization of the Riemann-Stieltjes integral in analysis. The integrands and the integrators are now stochastic processes, where H is a locally square integrable process adapted to the filtration generated by X, which is a Brownian motion or, more generally, a semi-martingale. The result of the integration is then another stochastic process. Concretely, the integral from 0 to any particular t is a random variable, defined as a limit of a certain sequence of random variables. The paths of Brownian motion fail to satisfy the requirements to be able to apply the standard techniques of calculus. So with the integrand a stochastic process, the Itô-stochastic integral amounts to an integral with respect to a function which is not differentiable at any point and has infinite variation over every time interval. The main insight is that the integral can be defined as long as the integrand h is adapted, which loosely speaking means that its value at time t can only depend on information available up until this time. Roughly speaking, one chooses a sequence of partitions of the interval from 0 to t and constructs Riemann sums. Every time we are computing a Riemann sum, we are using a particular instantiation of the integrator. It is crucial which point in each of the small intervals is used to compute the value of the function. The limit then is taken in probability as the mesh of the partition is going to 0. Numerous technical details have to be taken care of to show that this limit exists and is independent of the particular sequence of partitions. Typically, the left end of the interval is used. Important results of Itô calculus include the integration by parts formula and Itô's lemma, which is a change of variables formula. These differ from the formulas of standard calculus, due to quadratic variation terms. In mathematical finance, the described evaluation strategy of the integral is conceptualized as that we are first deciding what to do, then observing the change in the prices. The integrand is how much stock we hold, the integrator represents the movement of the prices, and the integral is how much money we have in total including what our stock is worth at any given moment. The prices of stocks and other traded financial assets can be modeled by stochastic processes such as Brownian motion or, more often, geometric Brownian motion. Then, the Itô-stochastic integral represents the payoff of a continuous time trading strategy consisting of holding an amount ht of the stock at time t. In this situation, the condition that h is adapted corresponds to the necessary restriction that the trading strategy can only make use of the available information at any time. This prevents the possibility of unlimited gains through high-frequency trading, buying the stock just before each uptick in the market and selling before each downtick. Similarly, the condition that h is adapted implies that the stochastic integral will not diverge when calculated as a limit of Riemann sums. Notation: the process y defined as before is itself a stochastic process with time parameter t, which is also sometimes written as y equals hx. Alternatively, the integral is often written in differential form dy equals h dx, which is equivalent to y minus y0 equals hx. As Itô calculus is concerned with continuous time stochastic processes, it is assumed that an underlying filtered probability space is given. The sigma algebra Ft represents the information available up until time t, and a process x is adapted if xt is Ft measurable. A Brownian motion B is understood to be an Ft Brownian motion, which is just a standard Brownian motion with the properties that Bt is Ft measurable and that Bt plus s minus Bt is independent of Ft for all s t0. Integration with respect to Brownian motion. The Itô integral can be defined in a manner similar to the Riemann-Stieltjes integral, that is, as a limit in probability of Riemann sums. Such a limit does not necessarily exist pathwise. Suppose that B is a Wiener process and that H is a left continuous, adapted and locally bounded process. If is a sequence of partitions of 0, t, with mesh going to 0, then the Itô integral of H with respect to B up to time t is a random variable. It can be shown that this limit converges in probability. For some applications, such as Martingale representation theorems and local times, the integral is needed for processes that are not continuous. If H is any predictable process such that 0th2 seconds less than infinity for every t0, then the integral of H with respect to B can be defined, and H is said to be B-integrable. Any such process can be approximated by a sequence Hn of left continuous, adapted and locally bounded processes, in the sense that in probability, then, the Itô integral is where, again, the limit can be shown to converge in probability. The stochastic integral satisfies the Itô isometry which holds when H is bounded or, more generally, when the integral on the right-hand side is finite. Itô processes. An Itô process is defined to be an adaptive stochastic process that can be expressed as the sum of an integral with respect to Brownian motion and an integral with respect to time. Here, B is a Brownian motion and it is required that sigma is a predictable B-integrable process, and mu is predictable and integrable. That is, for each t. The stochastic integral can be extended to such Itô processes. This is defined for all locally bounded and predictable integrands. More generally, it is required that H sigma be B-integrable and H mu be Lebesgue integrable, so that such predictable processes H are called X-integrable. An important result for the study of Itô processes is Itô's lemma. In its simplest form, for any twice continuously differentiable function f on the rails an Itô process X as described above, it states that f is itself an Itô process. Satisfying this is the stochastic calculus version of the change of variables formula and chain rule. It differs from the standard result due to the additional term involving the second derivative of f, which comes from the property that Brownian motion has non-zero quadratic variation. Semi-martingales as integrators. The Itô integral is defined with respect to a semi-martingale X. These are processes which can be decomposed as X equals M plus A for a local martingale M and finite variation process A. Important examples of such processes include Brownian motion, which is a martingale, and L-acute Vy processes. For a left continuous, locally bounded and adapted process H, the integral Hx exists, and can be calculated as a limit of Riemann sums. Let πn be a sequence of partitions of 0, t, with mesh going to 0. This limit converges in probability. The stochastic integral of left continuous processes is general enough for studying much of stochastic calculus. For example, it is sufficient for applications of Itô's lemma, changes of measure via Gersanov's theorem, and for the study of stochastic differential equations. However, it is inadequate for other important topics such as Martingale representation theorems and local times. The integral extends to all predictable and locally bounded integrands, in a unique way, such that the dominated convergence theorem holds. That is, if Hn, J for a locally bounded process J, then in probability, the uniqueness of the extension from left continuous to predictable integrands is a result of the monotone class lemma. In general, the stochastic integral Hx can be defined even in cases where the predictable process H is not locally bounded. If k equals 1, then k and kh are bounded. Associativity of stochastic integration implies that H is X-integrable, with integral Hx equals y, if and only if y0 equals 0 and ky equals x. The set of X-integrable processes is denoted by L. Properties. The following properties can be found in works such as The stochastic integral is a Cadlag process. Furthermore, it is a semi-martingale. The discontinuities of the stochastic integral are given by the jumps of the integrator multiplied by the integrand. The jump of a Cadlag process at a time t is xt minus xt minus, and is often denoted by delta xt. With this notation, delta equals h delta x. A particular consequence of this is that integrals with respect to a continuous process are always themselves continuous. Associativity. Let J, K be predictable processes, and K be x integrable. Then, J is Kx integrable if and only if Jk is x integrable, in which case, dominated convergence. Suppose that Hn, J, where J is an x integrable process. Then Hnx Hx. Convergence is in probability at each time t. In fact, it converges uniformly on compacts in probability. The stochastic integral commutes with the operation of taking quadratic covariations. If x and y are semi-martingales, then any x integrable process will also be x, y integrable, and hx, y equals h, x, y. A consequence of this is that the quadratic variation process of a stochastic integral is equal to an integral of a quadratic variation process. Integration by parts. As with ordinary calculus, integration by parts is an important result in stochastic calculus. The integration by parts formula for the Itô integral differs from the standard result due to the inclusion of a quadratic covariation term. This term comes from the fact that Itô calculus deals with processes with non-zero quadratic variation, which only occurs for infinite variation processes. If x and y are semi-martingales, then where x, y is the quadratic covariation process, the result is similar to the integration by parts theorem for the Riemann-Stieltjes integral, but has an additional quadratic variation term. Itô's lemma. Itô's lemma is the version of the chain rule or change of variables formula which applies to the Itô integral. It is one of the most powerful and frequently used theorems in stochastic calculus. For a continuous d-dimensional semi-martingale x equals and twice continuously differentiable function f from ρ to r, it states that f is a semi-martingale and this differs from the chain rule used in standard calculus due to the term involving the quadratic covariation xi, xj. The formula can be generalized to non-continuous semi-martingales by adding a pure jump term to ensure that the jumps of the left and right-hand sides agree. Martingale integrators. Local martingales. An important property of the Itô integral is that it preserves the local martingale property. If M is a local martingale and H is a locally bounded predictable process, then Hm is also a local martingale. For integrands which are not locally bounded, there are examples where Hm is not a local martingale. However, this can only occur when M is not continuous. The most general statement for a discontinuous local martingale M is that if one half is locally integrable, then Hm exists and is a local martingale. Square integrable martingales. For bounded integrands, the Itô stochastic integral preserves the space of square integrable martingales, which is the set of Cadlag martingales M such that E mount 2 is finite for all t. For any such square integrable martingale M, the quadratic variation process M is integrable, and the Itô isometry states that this equality holds more generally for any martingale M such that H2 M t is integrable. The Itô isometry is often used as an important step in the construction of the stochastic integral. By defining Hm to be the unique extension of this isometry from a certain class of simple integrands to all bounded and predictable processes, p-integrable martingales for any p greater than 1, and bounded predictable integrand, the stochastic integral preserves the space of p-integrable martingales. These are Cadlag martingales such that E is finite for all t. However, this is not always true in the case where p equals 1. There are examples of integrals of bounded predictable processes with respect to martingales which are not themselves martingales. The maximum process of a Cadlag process M is written as M*T equals subs T, Ms, for any p1 and bounded predictable integrand. The stochastic integral preserves the space of Cadlag martingales M such that p is finite for all t. If p greater than 1, then this is the same as the space of p integrable martingales by Dubs inequalities. The Burkholder-Davis-Gundy inequalities state that, for any given p1, there exist positive constants c that depend on p, but not m or on t, such that for all Cadlag local martingales M, these are used to show that if p is integrable and h is a bounded predictable process, then and consequently, hm is a p-integrable martingale. More generally, this statement is true whenever p2 is integrable. Existence of the integral. Proofs that the Itô integral is well defined typically proceed by first looking at very simple integrands, such as piecewise constant, left continuous and adapted processes where the integral can be written explicitly. Such simple predictable processes are linear combinations of terms of the form ht equals a1, t greater than t, for stopping times t and ft measurable random variables, a, for which the integral is this is extended to all simple predictable processes by the linearity of hx in h. For a Brownian motion B, the property that it has independent increments with zero mean and variance var equals t can be used to prove the Itô isometry for simple predictable integrands. By a continuous linear extension, the integral extends uniquely to all predictable integrands satisfying in such way that the Itô isometry still holds. It can then be extended to all b-integrable processes by localization. This method allows the integral to be defined with respect to any Itô process. For a general semi-martingale X, the decomposition X equals n plus a for a local martingale M and finite variation process A can be used. Then, the integral can be shown to exist separately with respect to M and A and combined using linearity, hx equals hn plus ha, to get the integral with respect to x. The standard Lebesgue-Stieltjes integral allows integration to be defined with respect to finite variation processes. So the existence of the Itô integral for semi-martingales will follow from any construction for local martingales. For a Cadlag square integrable martingale M, a generalized form of the Itô isometry can be used. First, the Dubs-Meyer decomposition theorem is used to show that if decomposition M2 equals n plus less than m greater than exists, where n is a martingale and less than m greater than is a right continuous, increasing and predictable process starting at 0. This uniquely defines less than m greater than, which is referred to as the predictable quadratic variation of m. The Itô isometry for square integrable martingales is then which can be proved directly for simple predictable integrands, as with the case above for Brownian motion. A continuous linear extension can be used to uniquely extend to all predictable integrands satisfying h2 less than m greater than t less than infinity. This method can be extended to all local square integrable martingales by localization. Finally, the Dubs-Meyer decomposition can be used to decompose any local martingale into the sum of a local square integrable martingale and a finite variation process, allowing the Itô integral to be constructed with respect to any semi-martingale. Many other proofs exist which apply similar methods but which avoid the need to use the Dubs-Meyer decomposition theorem, such as the use of the quadratic variation M in the Itô isometry, the use of the Doléan's measure for submartingales, or the use of the Burkholder-Davis-Gundy inequalities instead of the Itô isometry. The latter applies directly to local martingales without having to first deal with the square integrable martingale case. Alternative proofs exist only making use of the fact that X is CAD-lag adapted, and the set Hxt. H1 is simple previsible, is bounded in probability for each time t, which is an alternative definition for X to be a semi-martingale. A continuous linear extension can be used to construct the integral for all left continuous and adapted integrands with right limits everywhere. This is general enough to be able to apply techniques such as Ito's lemma. Also, a Kiyoshi inequality can be used to prove the dominated convergence theorem and extend the integral to general predictable integrands. Differentiation in Itô calculus. The Itô calculus is first and foremost defined as an integral calculus as outlined above. However, there are also different notions of derivative with respect to Brownian motion. Malyavan derivative. Malyavan calculus provides a theory of differentiation for random variables defined over Wiener space, including an integration by parts formula. Martingale representation. The following result allows to express martingales as Itô integrals. If M is a square integrable martingale on a time interval 0, t, with respect to the filtration generated by a Brownian motion B, then there is a unique adapted square integrable process alpha on 0, t, such that almost surely, and for all t, 0, t, this representation theorem can be interpreted formally as saying that alpha is the time derivative of M with respect to Brownian motion B. Since alpha is precisely the process that must be integrated up to time t to obtain Mount minus MO, as in deterministic calculus. Itô calculus for physicists. In physics, usually stochastic differential equations, also called Langevin equations, are used, rather than general stochastic integrals. If is a function of the xk, then Ito's lemma has to be used. An Itô SDE as above also corresponds to a Stratonovich SDE, which reads SDEs frequently occur in physics in Stratonovich form, as limits of stochastic differential equations driven by colored noise if the correlation time of the noise term approaches 0. For a recent treatment of different interpretations of stochastic differential equations, see for example